Good evening once again. My name is Arnold Young and I welcome you all back to the YouTube channel. Now, in the previous lecture, we compared flat interface with curved interface. Now, what did we say for flat interface? That is the pressure on the left side. One is the same as the pressure on the right side. And why is it so? If we said, assuming let's say the left side has air and then the right side has liquid. Now, if I select some molecule exactly at the interface, it will have that is intermolecular interaction with that is the other liquid molecules to form a hemisphere. Now, the intensity of that is the net cohesion, that is the intermolecular force of attraction between the liquid molecules will give rise to that is the shape or the curve or the curvature, right? The curvature of our sphere. Now, if there is no sphere created, the reason why the sphere is created is such that that is mostly the force of adhesion. If the left side of our interface is air, then the force of adhesion between the air and the water molecule exactly at the interface is less than that is the cohesion between the molecules at the interface and the liquid molecules exactly at the right side of the interface. But then to obtain a flat surface, then that is the net adhesion on the left side should be the same as the net cohesion force on the right side. That is for flat interfaces. We made those discussions in the previous lecture. Then we said for curved interface, the reason I have a curved interface is that there is actually a net force on. There's a net force right across the interface. So meaning the net cohesion force is greater than the adhesion force. That is how come we have a curved surface. So the curvature of interface. So the curvature of any interface of a liquid is as a result of that is the net cohesion force. We also derived the expression for gauge pressure of water droplets. We said gauge pressure of water droplets is giving us that is 4 times sigma divided by D or 2 times sigma divided by R. Now we said that for a liquid droplet in an air medium, air exerts pressure on the liquid droplet. Now the gauge pressure will be what? The gauge pressure will be the difference between the absolute pressure within our liquid droplet and the atmospheric pressure. Now the gauge pressure will try to provide the Beston force to do what? To separate our liquid droplets. So the gauge pressure provides the Beston force to separate our liquid droplets. The surface tension provides the joining force to join or try and join the interfaces of our liquid droplet. There was one thing I didn't say in the previous lecture. For liquids or for liquid droplets, they have only one interface. Liquid droplets only have one interface. That is it. Now, in today's lecture, I wanted to start with that is a droplet filled with gas immersed in some fluid mass. So let's just say we have that is a static fluid. This is the free surface of the fluid. Now the fluid above the interface of the fluid, we have air. So there is atmospheric pressure exerted on our fluid mass. Now the droplet, which is filled with gas, is located at some depth, which is h. The diameter of our droplet is capital D. Now, since the droplet is filled with gas, it will exert pressure that is all around the inner curved surface area of the droplet filled with gas. Now, similarly, The liquid will also exert pressure all around the outer curved surface area of our droplet filled with gas. So this is how the pressure distribution will be. So from the inside, the gauge pressure, I'm denoting with P1. From the outside, not gauge pressure, sorry, P1 is actually the absolute pressure within our droplet filled with gas. P1 is the absolute pressure within our droplet filled with gas. Now the absolute pressure exerted at the outside on the outer curved surface area of our droplet filled with gas is P2. I'm denoting that with P2. I'm denoting that with P2. Now, what do you think P2 is? P2, you remember from high school, P2 will basically be the sum of that's the atmospheric pressure, the local atmospheric pressure, plus the hot, plus the hydrostatic pressure as a result of this depth H, rho g H. And mind you, our fluid is of constant density. So this will be, that is the pressure exerted on the outer curved surface area. Now, P1 is greater than P2. We know this. We've already established that for a curved interface, that is the pressure on the concave side is always greater than the pressure on the convex side. So if we have a droplet, the inside is the concave side and the outside is the convex side. I've already told you this in the previous lectures. Now, there will be pressure discontinuity, yes. There will be pressure discontinuity. So you can find the change in pressure. The change in pressure will be, that's the greatest pressure, which is P1 minus P2. This is basically your gauge pressure. And it is, that is P1 minus PATM local plus rho GH. Now, we know that the gauge pressure is 4 times sigma over D. But then a student may ask, but then say, for this particular expression, gauge pressure expression, we're using it for liquid droplets, but this particular droplet is filled with gas. Why can we use this? We can apply this to any spherical droplet, provided that particular spherical droplet has a single interface. If the interface is 1, then we can apply this. Then we can apply this. So these two equations are applied to find, that is the gauge pressure within a droplet filled with gas. Within a droplet filled with gas. Now, the main work today I wanted us to look at is finding gauge pressure that is in a soap bubble in a gas medium. Now, let's just say I have a soap bubble, but I think I've told you that for liquid droplets, the interface is only 1. So if you could remember, that's the reason why, that is after sectioning the liquid droplet, we had only 1 interface and the surface tension lines were perpendicular to that 1 interface. You remember, so please keep this in mind. For liquid droplets, they do have only a single interface. Now, for soap bubble in a gas medium, Let us do the analysis. Normally, soap bubbles are filled with air, and air is a gas. So I can say a soap bubble is filled with gas. Now, since it is in an air medium, then there will be a local atmospheric pressure exerted all around the outer curved surface area. Since the gas is located within our soap bubble, then the gas exerts pressure all around the inner curved surface area. This pressure is an absolute pressure. The outer pressure is the local atmospheric pressure. Now we know the pressure at the concave side is greater than the pressure at the convex side. There will be pressure discontinuity. So the change in pressure, P1 minus PATM local, is basically your what? Your gauge pressure. Your gauge pressure. There's one thing you need to know. For soap bubbles, that is the same concept also applies here. Now for soap bubbles, the gauge pressure, if I draw the diagram again, the gauge pressure, so the net pressure will be the gauge pressure acting from the inside all around the inner curved surface area of our bubble. Now the gauge pressure is trying to burst our, that is soap bubble. The gauge pressure is trying to burst our soap bubble. The surface tension provides the joining force to join the interfaces of the soap bubble. So the gauge pressure, I said this in the previous lecture. So the gauge pressure provides the, that is bursting force. Now the surface tension provides the joining force. It is trying to join our soap bubble. So the gauge pressure provides the bursting force, the surface tension provides the joining force. So FB, bursting force, the joining force FJ, and as I said earlier, it is basically your surface tension force. Now, so the bursting force, let's say it has separated our bubble into two, and as I said, for a soap bubble, the interfaces are what? Two. So this is how the diagram is going to be. This is how the diagram is going to be, and the surface tension forces are going to be acting perpendicular to the interface. Going to be acting perpendicular to the interface. So the surface tension force are going to be acting perpendicular to the interface. But then mind you, the interfaces are two for soap bubble. So we'll have a surface tension force 1 on the first interface and a surface tension force 2 on the second interface. There's one thing you need to note. Now, for, as you said, yes, the bursting force is trying to separate our soap bubble. Now, if our soap bubble is to be kept intact, then at equilibrium, to be kept intact, the meaning our bubble will be in equilibrium, and at equilibrium, that is our surface tension force, which is the joining force, will be equal to my bursting force. So applying the equilibrium conditions, that is the sum of all forces along the x-axis is equal to 0, taking the forces with their signs to the right as positive. So now we'll have, that's the first surface tension force acting perpendicular to the first interface plus the second surface tension force acting perpendicular to the second interface minus our Beston force. Now, what is our surface tension force? Remember surface tension. Surface tension is equal to the force, the surface tension force divided by the length. Now, for the surface tension for the first interface, it will be the surface tension force for the first interface divided by the total length. And the total length is basically the what? That is, it is basically your what? Basically your, it is basically your what? Your circumference created by the larger diameter. Your circumference created by the larger diameter. So pi d, if my outer diameter or larger diameter is capital D, right? Now, then I can say that my surface tension force for the first interface will be sigma 1 times pi d. I can do a similar thing too. That is the second surface tension for the second interface. Surface tension force on that particular second interface divided by, so the second interface is created by my inner diameter. So the circumference of that particular inner diameter will be pi small d. So my surface tension force for that will be pi d multiplying sigma 2. Yeah, so I believe from here we can move on. Let us go to the next page. Then we can substitute. Okay, let me substitute everything in here. Then you can substitute all the expression into equation A. So let us do it. So now our first surface tension will be sigma 1 pi d plus second surface tension for sigma 2 pi capital D minus our Beston force is equal to 0. So this is our equilibrium equation. Now from equation B, we had, that is sigma pi d plus sigma 1 pi d plus sigma 2 pi small d minus our Beston force is equal to 0. Now, what is our Beston force? Our Beston force is basically our gauge pressure force. The Beston effect of the soap bubble is provided by the gauge pressure. So, a gauge pressure is equal to the Beston force divided by the projected area. What is my projected area now? After sectioning my soap bubble, the projected area is basically this area. That is the projected area. Basically, that area is our projected area. That is our projected area. And the projected area is created by the inner diameter. You can clearly see the projected area is created by the inner diameter. I can say my projected area is pi d small d squared on 4. So substituting in everything into the expression, what do we have? Sigma 1 pi d plus sigma 2 pi d minus, that is gauge, the Beston force will be the gauge pressure multiplying the projected area. So gauge pressure multiplying the projected area is equal to 0. There's one thing you should note. If the surface tension for the two interfaces are different, and that is the diameter, the larger diameter and the small diameter are not the same, then you can apply this equation. But mostly for soap bubbles, that is the larger diameter is almost the same as the small diameter. or we can make, or at least we can make that particular assumption. Now for soap bubbles also, that for the two interfaces, the surface tension is the same. Then I can say that my equation becomes sigma pi d plus pi d minus pg pi capital D squared is equal to 4. Then I can say my equation becomes this pi d squared on 4 is equal to 0. So my gauge pressure becomes what? My gauge pressure becomes, that is 8 sigma pi d on, that is pi d squared, which will be a sigma on d. So the gauge pressure for soap bubble is 8 times the surface tension divided by the diameter. That is, if the assumption is the inner and outer diameters are the same, and that is the surface tension for both interfaces are also the same. So this is the expression for finding the gauge pressure within a soap bubble. So now note, you remember I told you that for liquid droplets, the gauge pressure is what? 4 times the surface tension divided by, that is D, or 2 times the surface tension divided by R. Then we now know that for soap bubble, the gauge pressure for soap bubble, that is, it is 8 sigma on D, or 4 times sigma over R. Then I can say that for the same surface tension and the same magnitude of, that is, my diameter or radius, I can say one thing. I can say that A sigma over D, right, is equal to 2 times 4 sigma on D, and my 4 sigma over D is my gauge pressure of liquid droplet. My A sigma over D is my gauge pressure of soap bubble, or within a soap bubble. Then I can say Pg of soap bubble is equal to 2 times the gauge pressure within a liquid droplet. That is, if the surface tension for both is same and the diameter for both is also same. So I'll end the class here, and in the next lecture we'll talk about gauge pressure in water jet and introduce you to a beautiful concept called the Young-Laplace equation. So I'll give you a brief introduction to the Young-Laplace equation and use that to try to derive all these expressions. Have a wonderful evening.